Hello there, Mr. Sutton here, bringing you this lesson on derivatives and integrals of series. In this one, we're going to be taking derivatives and integrals of power series. To start this one off, we're going to start with a small review and some definitions. So when I talk about a series, I'm just talking about a sequence of numbers that's being added together. And for this part of the lesson, we're going to talk specifically about a geometric series, which is a series whose terms have a common ratio. So there's some starting term, which we'll call A1, and then we just keep multiplying by the same thing over and over again to get the next terms. So we've got A1 times R, and then we have A1R times another R, or just A1R squared, and we could keep going in this fashion as many terms as we want. So now that we've got that background, let's say that we have some function, f of x, that can be represented by a geometric power series given by this sigma expression below. See if you can remember sigma notation and write the first four non-zero terms from this thing, and then the general term for the series. All right, let's see how that went. So to expand something in sigma form, we just start with whatever our starting n value is, and start plugging in all the counting numbers from 0 to whatever the upper limit is until we can't go anymore. So we've got x to the 0, which is just 1, and then x to the 1, which is just x. Then we have plus x squared, x to the third, and they wanted the first four non-zero terms, so we've actually got that. We can now move on to writing the general term, which is just going to be this general expression in here with n. So we're just going to write plus dot 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 plus x to the n. And I'm going to write another plus dot 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 because my upper limit of summation is infinity. So I have to show that this keeps going. All right, now that we've written this out, got a little review of sigma, our next task is to write this f of x as an actual function rather than just an infinite series. So pause the video and see if you can figure out how to express this geometric series as a function. All right, so on this one, if you want to write something as a function, you basically are just trying to figure out an expression that represents the sum of this entire infinite series. Now that seems like it's kind of a tall order, but since this is an infinite geometric series, that means we actually have a formula for the sum of this thing. This is just going to be a1 over 1 minus r. So on this problem, a1 is just this 1 here. That's just our first term. R, the thing we keep multiplying by, is x. And you can see that because x is being raised to an exponent in here. So r is just x. Plugging all that in then, we can just write f of x equals 1 over 1 minus x. For this example, given this f of x that we saw in the warm-up, we want to write the first four non-zero terms in general term of a power series for f prime of x. So we're just going to take the derivative of this series. Well, we're just going to start by writing out f of x. So again, we had 1 plus x squared plus x cubed, and so on and so forth until we have x to the n with a bunch of dot dot dots. But now, before we go ahead and start taking derivatives, let's think ahead a little bit. They said we need the first four non-zero terms. Well, if you take the derivative of 1 here, that's actually going to be 0. So you're not going to have four non-zero terms after you take the derivative. For that reason, it's a good idea to write out one more term than you think you need in order to do these f prime calculations. So I'm going to put a plus x to the fourth in here just to cover my bases and make sure I have enough terms when I take the derivative. Okay, all we have to do now is just differentiate term by term. Take a moment to do that. So we've got f prime of x equaling 1 plus 2x plus 3x squared. The power rule is fun, right? Plus 4x cubed. And now for the general term, this n gets treated as a constant, so we can just use the power rule on this as well. So this is just going to be n x to the n minus 1 with all the dot dot dots that go with it. So this is one way of doing it. Now, you may sometimes need to differentiate the sigma expression directly. For example, if you're trying to match multiple choice that just has sigmas for answers. So this process is pretty much the same as what we did for our general term here. We're just going to have n times x to the n minus 1 with all this sigma stuff attached. There's only one small difference. You'll notice I didn't fill in this n equals down here yet. So one big difference between sigma notation and expanded form, you don't need to tell us what the starting n value is. Even though we write n over here, this whole thing just has to work for some starting n value, and we kind of leave it up to the reader to figure out what that starting value is. With sigma form, you do need to specify the starting n value. Now, what should it be? If we let n equals 0, like in the original up here, we're just going to have n times x to the negative 1, which is kind of bad news. So we don't want negative exponents here. So you're going to have to change the start value to avoid those negative exponents. Now, why don't we want negative exponents? Well, if we have x to the negative 1 and we're dividing by x, that means we might potentially be dividing by x equals 0. So we're going to make this n equals positive 1, so that my very first term is just going to be 1 times x to the 0, which is just going to give me this 1 that I had up here. For this next example, given this different f of x now, we want to write the first 4 non-zero terms in general term for the integral from 6 to x of f of t dt. So this is kind of the same idea, except we're doing integrals instead of derivatives. So again, let's start by writing out f of x. And when you're doing this, I recommend you keep this in x minus a form. It'll just make this whole process easier. So pause the video and do that. And you can just write out the first 4 terms in the general power term. Since we're integrating, we're not going to differentiate anything away. All right, let's see how that went. So our first term, when we plug in 0 for n, this is just a positive, and we just have all of this to the 0, which is just 1, which is kind of convenient. Now for n equals 1, this is going to be negative x minus 6. And then for 2, we're going to have a positive x minus 6 squared. And then you can kind of see the pattern here. This is actually another geometric type of pattern. So we're doing a minus x minus 6 to the cubed, and plus x minus 6 to the 4th would be the next term. Eventually, we have our general term there. All right, at this point, we're just going to go through and integrate this thing term by term. You just have to be careful to use the variable of integration when you're actually writing out your evaluation box. So up here, our variable of integration is a t, not an x. So if you're putting all this in an evaluation box, the first thing I'm going to have to write is not x, but t. And then after that, I've got this whole parentheses to the first power. That bumps up to a 2. Dividing by that, I've got minus 1/2 t minus 6 squared. And then pause the video and do the rest of these out here. All right, so next I've got 1/3 x minus 6 to the 3rd. This will be minus 1/4 t minus 6 to the 4th. And then finally, for this one, I've got, let's see here, I'm just going to put this in the numerator. So I'm going to have negative 1 to the n over n plus 1 times t minus 6 to the n plus 1. I'll put a little dot, 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 because this actually just keeps going. And again, I'm evaluating all of this from 6 to x. So the very first thing I'm going to get when I plug in here, I'm plugging x in for all these t's. So I'm just rewriting all of this stuff with x's instead of t's. So literally, I just cut and pasted and put x's in there. I've got x minus 1/2, x minus 6 squared plus 1/3, x minus 6 cubed, so on and so forth. But now you have to be careful, because if you plug in 6, you'll notice that a lot of these terms are getting zeroed out, which is great. But plugging in the lower limit sometimes gives us non-zero terms. For example, if you plug in 6 to this very first term over here, t, you're just going to get 6. So we're going to be subtracting that 6 that you got by plugging 6 in for t. And I'm just going to put this minus 6 at the beginning here. But now the rest of these, again, 6 is going to zero everything else out onto the infiniteth term. So this ends up being our series. For this last problem, we're given this f of x function. And based off of this, we want to write the first 4 non-zero terms in general term of a power series for g of x and h of x. So you might be wondering, well, how is f of x supposed to help us with all of that? Pause the video and take a moment to compare f of x with these other two functions. See if you can figure out the relationship between f and these functions. Did you spot it? So it might have taken a little bit of doing here, but you might have noticed that g of x is actually the derivative of this thing. And you might need to, move this 1 minus 2x up to the numerator with a negative 1. But if you do that and take the derivative, you actually get g of x. By the same token, if you take the antiderivative of f of x, you'll notice that you end up getting this h of x function over here. So this is the key, is recognizing that we have this derivative integral relationship. So if you want to write the series for g and h, it would be helpful if you already had the series for f of x, and then you could just differentiate or integrate that series. So first things first, let's write out a series for f. Now how do we do that? This is a little bit of review from before. This is in a1 over 1 minus r form. This is essentially just the function representation of a geometric series. If you have something in a1 over 1 minus r form, you can convert anything in that form to a geometric power series. Pause the video and write a geometric series based off of this. All right, so our first term is 5, and we're multiplying by 2x each time the thing that's being subtracted from 1. So this is 5 times 2x, or 10x. Then we've got 20x squared, 40x cubed, and now thinking ahead, if we're going to have to take the derivative of all this stuff to get g of x, then we might as well go one more term out here and get 80x to the fourth. Finally, for the general term, you've got 2 and x that are being multiplied each time, so that's a 2 to the n and an x to the n, and we've also got this 5 at the beginning of everything. So I'll write 5 times 2 to the n x to the n. All right, now to get g and h, as we said before, for derivatives integrals of a function like we have here, you just have to differentiate or integrate the original series. So pause the video and let's get the g function here. Now again, g is really just f prime. So I'm just taking the derivative of the f series to get the g series. So I've got a 0 for that first term, and then this next term is going to be a 10, followed by 40x, 120x squared, 320x cubed, and now over here, we're just multiplying by the n that's on the x here. So this is 5n times 2 to the n times x to the n minus 1. And I just put the n in there, whatever. It doesn't really matter where you put it as long as it's getting multiplied. All right, time to go the other direction. Now we said that h was the integral of the f function, and we're going to write this as integral from 0 to x of f of t dt. And just in case you were wondering how I know that my lower limit of integration should be 0 as opposed to anything else, if we look at all these terms in the f function, we just have x's. We don't have like x minus 6 or something like that. In that case, you'd have a different number if it were like x minus something. But if you just have x, then your lower limit's going to be 0. All right. So the other thing you might have noticed is if you're thinking ahead about when you take the antiderivative here, all of your antiderivative terms are going to end up with x's in them, so that when you plug in this lower limit of 0, you're going to end up zeroing out every single term. If you know going into this that your lower limit zeroes everything out, you can actually skip the evaluation box with the t's in it and just go straight to the answer. So our first term we could write out, for example, we can just go straight to writing out 5x. Now pause the video and write out the rest of it. All right, so we've got, this is going to be x squared, and 10 divided by 2 is 5, so 5x squared. Next, we're going to have 20 over 3x cubed. And this is going to be, let's see, 40 over 4, that's just 10x to the fourth. And they just wanted the first 4 non-zero terms, so we're not going to worry about this next term here. We're just going to go straight to the general term. So this is going to be 5 times 2 to the n over n plus 1 times x to the n plus 1, ... So that's it for derivatives and integrals of series. Until next time, this is Mr. Sutton signing off.